In this video, I'll be working through a past paper question for grade 12 physical sciences on vertical projectile motion. So here we have a question 2, and 2.1 says a person throws a ball upward into the air with an initial velocity of 15 meters per second. Ignore the effects of air resistance. Now, the thing with this question is that we don't actually have a diagram to work with. So for questions like this, without a diagram, it's actually best if you draw a diagram of your own, since for vertical projectile motion questions, it's a lot easier to understand what to do and what's going on if you can visualize it. So we will help ourselves with that with the aid of a diagram. So here's my diagram. Here is the little person, here's the ball, and what's happening is that this object is being thrown upward. And to understand the motion of the object, as the object moves upwards, its velocity is going to decrease. And its velocity decreases to 0 when it reaches its highest point. From there, it's now going to fall down. So its velocity starts to increase, but in the negative direction. So this picture is a good representation of the situation that we have at hand. What we also can do is fill in the given information. We know that initially this ball was thrown up with 15 meters per second as its velocity. And another bit of information that we always know is that when an object is at its highest point, its velocity is equal to 0. So this is what we have to start off with. 2.1.1 says, what is the physics name given to any object like the ball above, where only the gravitational force of the Earth is acting on it? And that is a projectile. So a projectile is an object that is in free fall. So free fall is where the only force acting on the object is the force of gravity. So it is only under the influence of gravity. So the answer to 2.1.1 is projectile. Now 2.1.2 says calculate how high it goes up before coming down. So what's happening here is that this ball is being thrown upwards. So from the person's hand up to the highest point, we are concerned with how high up it goes. So we are concerned with the displacement of this object, which is going to be in the positive direction. So this is what we need to calculate, delta y. Now, based on the information at hand, what we have is VI as 15, positive 15, because remember, we take up as positive, down as negative. We've got VF as 0 meters per second. We need to calculate displacement. We don't have any information about time, and we know that acceleration is negative 9.8. So looking at our formulas, now these are the formulas from your formula sheet, and the formula that is the most appropriate here is the second one. VF squared is equal to VI squared plus 2A delta Y. So the formulas usually come with delta x in it as displacement, but we change it to delta y since we are working in the vertical direction. So here is our formula. Let's substitute. We know that VF squared is 0. So 0 squared is 0. Then VI is a positive 15 squared plus 2 into. Acceleration is the same thing as g, which is the acceleration due to gravity. Gravity always acts down. So that's going to be negative 9.8, and delta y is our unknown. So direction in this section is extremely important. We have to have the correct sign with a value according to its direction. Now simplifying here, we have 0 is equal to 15 squared is 225. 2 times negative 9.8 is going to be negative 19.6 delta y. Now since we're trying to solve for delta y and that value is negative, let's take it over to the left. So that becomes positive 19.6 delta y is equal to 225. Now to make delta y the subject, we are just going to divide both sides by 19.6. So that gives me 11 point, well, I have 479, so it becomes 48 meters. So that is our delta y here. Now 2.1.3 says calculate how long the ball is in the air before it comes back to the hand. So now this is referring to time. And what they actually want is they want the time. So from the time the ball is thrown and it goes up to its highest point and it comes back to the person's hand. So remember, this is just how the motion is displayed. But what's actually happening here is the person is throwing the ball straight up, it's going up to its highest point, and it's coming back down, where the person is actually catching it. But when we draw a diagram, we generally draw the displacement curved so that we are able to see what's actually going on. So what we're concerned with here is the time taken for the ball to go up to its highest point and come back to the person's hand. Now this is what we can actually do, and I'm just going to move the displacement information to the left so that it's out of the way. Okay, so now we can ask ourselves, what is going to be our approach to answer this? To get the time taken for the ball to go from the time it's thrown from the hand, so the starting point, to the highest point and back to the person's hand. Now notice that this forms a parabola. And what we know about a parabola is that it is symmetrical on either side. So the time taken for this ball to go from the starting point to that highest point is the same as the time taken for it to go from its highest point back to the starting point. For example, if it took 5 seconds for the ball to go up, it should take 5 seconds for it to come down. So we know this from maths, right? That a parabola is symmetrical. So what we can do is we can calculate the time taken for the ball to go from the starting point to the highest point, and whatever answer we get, we can multiply it by 2. So that's the approach that I'm going to take. I'm working from the starting point to the highest point. Now, since I need time, so I'm looking for delta t. I've got VI, I've got VF, I know A, and I need delta t. We can work with the first formula. That will actually be the easiest one to work with here. Okay, so VF is 0, VI is a positive 15, A is negative 9.8, and we're trying to solve for delta t. Let's take this negative 9.8 term over to the left. It's going to become positive. And now to get delta t alone, we're going to divide throughout by 9.8. That should give you 1.53 seconds. But remember, that 1.53 is only the time taken to go from the starting point to the highest point. So we are going to multiply that by 2. So we're going to take this answer, 1.53 multiplied by 2, and that gives you 3.06 seconds. So this is actually the total time. So let's just write that down. Total time. Okay, so what does that mean? It means that the time taken for the ball to be in the air, meaning from the time it was thrown up till it went to its highest point and came back to the hand, that entire duration. So once it reached this point again, that took 3.06 seconds. Okay, so it's actually good that once you calculate values to fill it in on your diagram. It helps a lot, especially with the section where we have a lot of follow-up questions. So as you calculate values and you fill it in on your diagram, you will also make sense of those values, whether they are correct or not, especially with values like displacement and velocity where they are vectors. Okay, we're going on to 2.1.4. It says calculate the time it takes the ball to pass a point of 8 meters above the person's hand. So 8 meters above the person's hand. Now let's figure out where that is. So if from the person's hand to the highest point was 11.48 meters, and we're looking for 8 meters, we can estimate 8 meters to be, say, somewhere here. Okay. So if that is going to be 8 meters, what are we concerned with? We want to know the time it took for the ball to move 8 meters above the hand. So for this motion specifically, we want to know what the time was. Now for this situation, the information that we have is we have VI, but 8 meters above the hand, we don't know what the speed was that the ball was moving at. So we don't have VF. We have VI, we have delta Y, we have A, but VF is unknown. So for situations where VF is unknown, the only formula that we have without VF in it is this one. Delta Y is equal to VI delta T plus half A delta T squared. So delta Y here is going to be 8, since the object moved 8 meters above the hand. VI is 15, it is positive 15 because the ball was thrown up, but delta T is unknown. Plus a half into A is negative 9.8, delta T is unknown again. Now let's simplify. We have 8 is equal to 15 delta T minus 4.9 delta T squared. So what we notice here is that this is giving us a trinomial, a quadratic trinomial. So let's get it in standard quadratic format. I'm going to take all of my values over to the left and put them in the correct order as well. So how do we solve this? We've got standard quadratic format. We can use the quadratic formula. Here's our quadratic formula from maths, and we're now going to substitute our values. So here our B value is negative 15, our A value is 4.9, and C is 8. Now solving here, we're actually solving for delta T, so we're going to have delta T is equal to, I've got 2.37 seconds, or delta T is equal to 0.69 seconds. Now normally in these questions, we get a positive time and a negative time, and where we have the negative time, we say that it is not applicable. And we take the positive time as an answer because time is a scalar. But here, we've got two positive answers, and both of them are acceptable. So why is it that we have two values? If we refer back to our diagram, we realize that there are actually two instances where the ball is 8 meters above the person's hand. That is the first case, like what we have here on the diagram. But when the object goes up to its highest point and comes back down, at some point here, it is also going to be 8 meters above the person's hand. So there's two instances here, which is why we've got one time value, which is smaller, the 0.69 seconds. So the 0.69 seconds indicates the first time that the ball is 8 meters above the hand. And the 2.37 seconds indicates the second time when the ball is 8 meters above the hand. Because obviously, once it moves up to its highest point and comes back down, more time has to pass, more time has to lapse by for it to get to this point. Okay, so how do we show this? We can underline both answers because they both are acceptable. So these are our two answers for that question. Now 2.1.5 says draw a position versus time graph indicating the following times. So we need the time at the point of projection at 8 meters above the hand, at the maximum height, and back at the thrower's hand. Okay, quite a bit of information that they are requiring, and let's start off by drawing our axes. So here we've got time on the x-axis. Time always goes on the x-axis because it is the independent variable. We have position on the y-axis, and we label our axes, and we always show our units in brackets. Now, what's happening here is that the object is being thrown up from the person's hand. So we don't know the height from which it is thrown up. We don't know how high up above the ground the person's hand is. So for this question, it's actually best if you take the person's hand as your 0 point. So your entire x-axis would be that point. So we're going to draw a graph above that. So we're actually going to have this parabolic shape above the x-axis. So we're going to start at 0. And I'm just going to do the basic outline of this graph first. So from 0, the ball is being thrown up. It's going to go up to its highest point. At its highest point, it falls and it comes back down. So this is the shape of our graph. Now, what values do we know? With regards to displacement, we know from the starting point to the highest point. So here, okay, let's do that better. The displacement was, what did we get it to be? 11.48 meters. So 11.48. Then they wanted you to indicate specific time values, and it's basically all the time values that we calculated. So we had calculated the time taken for the object to go from the hand to the highest point. So there's our highest point here, and we calculated that took 1.53 seconds. We also calculated the time taken for the entire duration, for the entire motion of the object, which was 3.06. Then we had two other time values. We had time values for 8 meters above the hand. So let's indicate that 8 meters above the hand, which I'm going to take somewhere here as 8. And actually remember, there were 2 points, right? So from the graph, you can actually see it a lot clearer that there are 2 instances where the ball was 8 meters above the person's hand while it was moving up and also on its way back down. So let's fill in our time values for those. The first one we had was 0.69, and the second one, I'm just going to move a few things here. The second one was when it was on its way down, and that value was 2.37. So this is our complete position versus time graph with all the requested values. Now we have a question 2, and this is based on new information entirely. It says a stone is dropped from the roof of a building. A second stone was thrown from the same height, straight down 2 seconds after the first stone had been dropped down with an initial velocity of 30 meters per second. After having covered the same displacement, the 2 stones reached the ground at the same time. How long did it take the second stone to reach the ground? So let's use this information and create a diagram for ourselves. Also here we have two projectiles. So this is going to be a question where we are most likely going to solve simultaneously. This is your level 4 question in the section. Okay, so here's our situation. Here is our two stones. Now let's fill in information. The first stone is dropped, meaning that its initial velocity will be 0 meters per second. However, the second stone is thrown. So the second stone is thrown downwards. They are both moving downwards. Okay, so just arrows to indicate that might help. So we said the second stone is thrown, but it is thrown with a velocity of 30 meters per second. Now velocity is a vector. So since it is thrown downwards, its initial velocity is going to be negative 30 meters per second, since we are taking downwards as negative. However, your second stone is thrown 2 seconds later. Okay, so let's just make a note of this. It's thrown 2 seconds later, meaning that, for example, if it took stone A, I'm just going to call the stone A, if it took stone A 10 seconds to reach the ground, it would have taken stone B 8 seconds to reach the ground because it was thrown 2 seconds later, and we know that they reached the ground at the same time. So even though it was thrown 2 seconds later, that 2-second delay does not make a difference because they reached the ground at the exact same time. So that's also something good to take note of, right? For your second stone, whatever time it took to reach the ground, your first stone took 2 seconds longer. So to reach the ground, it would be delta t plus 2 seconds because it had that extra 2 seconds head start. Okay, so currently this is all the information that we have. We don't know what the displacement is. We don't know what their final speeds are. Their final speeds would be different. We don't know what that is. We only know their VIs, the initial velocities. We know acceleration is negative 9.8. And we know that for the first stone, the time that it took to reach the ground would be delta t plus 2. So the extra 2-second head start that it had. And your second stone, we're just taking that as delta t. This is what we have to go on with. Now, since we don't know what VI is, sorry, I actually meant VF. Since we don't know what VF is, there's only one formula that we can use. That is going to be this formula, delta y is equal to VI delta t plus half a delta t squared. And just to remind ourselves, what exactly are we trying to calculate here? How long did it take the second stone to reach the ground? So we want to know the second stone that we have. We are solving for this delta t. That's what we want to calculate. Okay, so I'm going to start off by working with the first stone. I'm going to substitute the information, then I'll go on to the second stone. Here is our formula. Delta y is unknown. That is going to just stay as delta y. So stone 1 was dropped. And when an object is dropped, its initial velocity is 0. So the first term is 0. Then we have a half into negative 9.8. And our delta t is going to be delta t plus 2 because it had that extra 2-second head start. Okay, so another thing that you can do, because you are substituting and you know that the objects are going to move downwards, the delta y on the left is actually negative because it's a negative displacement. Okay, so it's a negative delta y. Simplifying what we have, we're going to have negative 4.9. I'm going to keep this bracket as is. Okay, I'm not expanding just yet. So this is what we have to go on with stone 1. Now, let's work with stone 2. Same formula. Again, for stone 2, its displacement is downwards. And the thing here is that stone 1 and stone 2 have the exact same displacement. They are both falling from the same point above the ground. They are both falling from the roof of the building. So they will fall the exact same distance for them to reach the ground. So this is also going to be delta y on the left. But remember, stone 2 was thrown. So its VI is going to be negative 30 delta t plus a half into negative 9.8 delta t squared. Okay, let's simplify. So our next step is to equate these equations together, because you're going to notice that they are both equal to negative delta y. So we can equate them to each other. That's going to be our next step. So here's what we have. Now we need to simplify this. And we've got this bracket that is squared on the left-hand side. So we have to expand that. We've got a binomial squared. It's going to result in a trinomial. Here's what we have once we expand. Now we're going to take this negative 4.9 into the bracket, and it's going to multiply with all three terms. Okay, here's what we get once we multiply in. Negative 4.9 times delta t squared, we've got that here. Negative 4.9 times positive 4 delta t, we get negative 19.6 delta t. And negative 4.9 times positive 4, we get negative 19.6. Now we need to gather like terms. So let's get all of our terms that have delta t over to the left. And what we notice is that we've got this negative 4.9 delta t squared on both sides. So when we take the term from the right over to the left, they're actually going to cancel out with each other. When I take this negative 30 delta t over to the left, it's going to add. So I've got minus 19.6 delta t plus 30 delta t. I get 10.4 delta t. I'm going to take this negative 19.6 over to the right. It becomes positive. And lastly, to get delta t, we are going to divide both sides by 10.4. So I get 1.88 seconds. So that is the correct answer. That is how long it took the second stone to reach the ground. So that is actually what the question wanted. Please remember to like, subscribe, and turn on your notifications for more content.